Hello and welcome to lesson number 3 in Unit 7, Exponential Functions in our Grade 11 University College math class. So today we're looking at applications of exponential functions. This is a nice sort of next step away from exponential growth and exponential decay. The first part of this lesson is just sort of a recall. It talks a little bit about the formula that we've been developing. And I always like to make a little addition to our formula here where, yes, this is our basic formula, but just always to keep in mind that we're talking also about instances where we might have, a rational exponent where the numerator represents how much time has gone by and the denominator represents how long it takes for B to happen, whatever B happens to be. So it looks at that. It reminds you that a growth factor, this is what's highlighted in green, we call something a growth factor when our B value is larger than 1, so something that's going to be growing. We call something that's between 0 and 1, so proper fractions, we call them decay factors, since they will get smaller as time goes along. And when the B value is equal to 1, it is neither growth nor decay. It's going to just maintain itself at its current size, because 1 to the exponent anything is going to be 1. So that is something just to keep in mind as we head into today. And today is really looking at a distinction between what we would call growth and decay factors versus growth and decay rates. So I'm going to just scooch this up. I'm going to let you guys copy down the next two examples that we're going to be looking at. They're sort of filled in. And when you're, hit pause. When you're done, come on back and I'll talk you through what's going on here. Okay, you're back. You've got these copied. Let's read. So it says, the difference between the growth/decay factor and 1 is always called the rate of growth or decay. Often rates of growth and decay are given as a percentage. So we've been talking about growth and decay rates already, but the values that we've been looking at have been confined to either whole numbers, so like doubling or tripling or quadrupling, or specifically a half-life where our B value is equal to 1/2. Today we're going to be looking at how do we incorporate a percentage increase? Because again, recall, percentages are being applied to A values, and that will always make the outcome different but proportionally the same, which I guess isn't a very clear way of saying that. I guess what I mean is like 10% of 60 is different than 10% of 10. The amounts of change are different. They're always 60%, but that 60% depends on what you're starting with. So that's where we introduce this idea of growth factors versus growth rates. Maybe the best way to illustrate this is to show you an example. So here's example number 1. To model growth, we add the growth rate to 1. This gives us a growth factor. So I've developed a scenario here where I have the Abbey Road Beatles album on vinyl, mint condition. I inherited this. It was $15,000 back when I did this lesson the first time, which apparently, as we learned in an earlier lesson, was quite a long time ago. And it sees a 2% increase in price per year approximately. And we can answer questions like how much will Abbey Road cost or be worth in 7 years if we use this equation over here. So I've got the equation kind of set up. As I said when I was reading the description, we take whatever our growth rate happens to be and we are going to add it to 1. Now why 1? Well, the 1 in this bracket, it represents, I'm just going to make a little note of this, it represents 100% of the original amount. So you would consider that if I had, whatever, $15,000 and my growth rate was B, my B value was like equal to 1, then that would be 100%. It would never actually change. So that 1 there represents 100% of whatever we were starting with. This adding a percentage on is a way of including this growth into our equation. And I do always like to add that time, but I'm also going to make it over h, how long it takes for whatever growth to happen. So let's start to create this equation. So we have a $15,000 product increasing at 2% per year. How much will Abbey Road cost in 7 years? So let's start to develop this. The cost of Abbey Road in 7 years is still going to be our unknown. The A value is the initial amount. How much did Abbey Road cost when we started this question? So it was at $15,000. 1 plus, now the percentage increase was 2%, and I'm going to write this out in sort of a different way. 2% is 2/100ths, if you want to write it like a fraction. The time is going to be 7 years. And how long does it take to increase by 2%? Well, it said that it increased at 2% per year, so that's per 1 year. It doesn't really change this particular equation, but again, we're just doing it in there to sort of model good practices. Now, I'm going to make just a little change here. It's not a change, I'm going to include a calculation here, where this is now 1 plus 0.02. That's how we express 2/100ths as a decimal, is 0.02. Now at this point, you could type it into your calculator. I typically advise students to just do that little bit of fairly straightforward, sorry I lost a 0 here, there it is, to do this little bit of very straightforward math before they do the calculation, just to save the calculator any woes it might have in not being able to interpret what you want it to do. And I add the 1 and 0.02 together. So now I'm just going to type this into my calculator. So there's my 15,000 times 1.02 to the exponent, and I'm going to, I normally would open a bracket, do 7 divided by 1, but I'm just going to pop in a 7 this time because it's pretty straightforward, and that's going to give me y is equal to approximately $17,230.28501, so we're going to go 29 cents. So that's what Abbey Road will be worth in 7 years' time. And no, I'm not going to sell it. It was given to me, or I inherited it, and I'm not going to sell it, but that's what it's worth. So, growth factor, we have that 1 plus the percentage increase. Example number 2, this time we're going to model decay, where we subtract the decay rate from 1. This gives us a decay factor. So, I do not own a Toyota Prius, but there you go. So a Toyota Prius 2014 costs $35,000. It depreciates at a rate of 3% per year. How much will the Prius be worth in 5 years? So same idea here. We're going to build ourselves an equation. And this time, because something is losing value, we are going to be subtracting that amount from it. So let's start to build this equation again. So we have depreciating it at 3% per year. So here our y value, oh, that's the highlighter. Our y value is going to be the cost of the Prius at a certain amount of time, in this case 5 years. The original cost of the Prius was $35,000. 1 minus, and it goes down by 3%, so again that's 3 over 100. And the time is 5 years. And how long does it take to go down by 3%? It goes down by 3% in every 1 year on average. So we're going to just put our denominator in there as 1. I'm going to do, again, the same calculation I did before, where we have 1 minus 0.03 to the exponent 5. Again, I typically encourage students to do this calculation. It actually just saves you bracketing if you actually take the 1 and minus 0.03, which is 3%. And again, we didn't mention it, but this 1 represents 100% of that $35,000 that we start with. So if I take 1 and I minus 0.03, I end up with 0.97 to the exponent 5 over 1, or just 5. And now we can actually do this calculation. If you don't do the if you don't do 1 minus 0.03, again, you can just type it in exactly like that. If you're confident with your bracketing on your calculator, you should get the same answer. So it's no big deal. Okay, so we're going to type in 35,000 times 0.97 to the exponent. Again, I'd open a bracket here, but it's just 5 divided by 1, which is just going to be 5. And that's going to equal approximately $30,055.69. So that's how much my Prius will be worth, or a Prius will be worth in 5 years' time. So again, what's the big learning here? It's actually a really short lesson. The big learning is that when you have percentages of increase and percentages of decrease, you either add them or subtract them from 1 to develop that equation that we've been using to model exponential growth or decay. That y equals a times b to the exponent t over h. That b value, it doesn't have to be doubling as 2 or half-life is a half. You can either add a percentage like 2% with Abbey Road, or we could subtract a percentage like we did with the Prius. It has to be a decimal, and that's the important part there. So we need to convert 2%. We're not doing 1 plus 2 because that's 3, and that will give you tripling. We want to just make sure that we are changing that percentage into a decimal, before we add it or subtract it from 1. And then we just do the calculation, same as before. So I'm going to stop the lesson here. Like I said, it's really a short lesson today. You don't even have any homework. The homework is the rest of the note, which you'll see here in these problems. So we're going to talk about this in the second part of this lesson. We're going to crank through the first page of this, and then you can do the second page for homework. So we'll see you in part 2.